Gauss's theorem, or the divergence theorem. So let's just start off by saying what the theorem's about, or what the theorem is. Now, this is another relation between a flux interval or a flux integral and another type of integral. And so the other type of integral turns out to be a triple integral. And the thing that goes inside of a triple integral, remember, a triple integral that we've studied has to have a scalar function inside. And capital F right now is a vector field. So to get the scalar function, we're going to take a look at the derivative of the vector field. And remember, there's two derivatives for the vector field, the div and the curl. So since this is called the divergence theorem, it's the div. So this is the actual statement of the theorem, and there's a few conditions and clarifications about what is what. And so we can, usually that's done beforehand, but we'll do it afterwards. So here we're looking at F as a vector field in 3 dimensions. So F goes from R3 to R3, and then now we need to figure out what's up with those surfaces. And the solid, E is a solid, S is a surface. So S is a closed surface. So remember, Stokes' theorem had an open surface where it had a boundary. This is a closed surface where it is actually the boundary. E is a solid with boundary S. So it's a solid, and a solid is a 3-dimensional object, and it turns out that S this time, that closed object, is your boundary. So sometimes this is rewritten as the triple integral of E of the div of F dV is equal to the flux integral over, now instead of saying S, I would just slightly change the notation to the boundary of E, which is a closed surface, S, of the original vector field, and it's a flux. And it's kind of like a line integral, and if you're talking about a closed region, then this isn't very common with flux integrals, but technically you can put a circle around the flux to say you're integrating over a closed surface. And orientation going in the positive direction is usually the outward orientation. So we could mention the outward orientation for this example. Okay, so that's the theorem, and that's a big deal theorem for us. And so I guess the next thing to do is take a look at some examples and work through it, and then take a closer look at the theorem and see how we can play with it a little bit. This is our last big theorem, and after this we're going to try to unify all these theorems that we've been talking about. And all these theorems that we've been talking about is really just the fundamental theorem of calculus in different modes, different perspectives, things like that. So let's take a look at an example. This looks like an innocent-looking example. Oh, actually, this example says to verify that it's true. So this would be a good example to start with. We can do both sides. We can do the flux integral and do the surface integral, not the surface, but the triple integral, and then see which one looked easier, and hopefully we get the same answer. And then we'll compare. So verify the divergence theorem is true of the vector field of a given region E and give the flux. So let's start with the flux integral. We'll do the flux on this page, and then the next page we'll do the triple integral of the other half of the divergence theorem. Okay, so E is a cube bounded by, so we need to take a look at our surface. E is a cube bounded by the planes x is equal to 0, so that's yz plane, x is equal to 0, y is equal to 0, and z is equal to 0. So it looks like the corner of the cube is on the corner, on the origin, and it goes from 0 to 3 in the x, 0 to 3 in the y, 0 to 3 in the z, and so I think this is the cube that they're talking about. Okay, so now as a flux integral, we need to look at this as 6 different surfaces. So already our problem got difficult. So already we're dealing with surfaces. So let's take a look at the surfaces. Let's start with I think might be easy surfaces. I don't know. And so let's start with the x is equal to 0 surface, S1, x is equal to 0. And when x is equal to 0, your limits are with y and z, so your y is y and your z is z, or uv, depending on what you want to do. So x is equal to 0 is your surface, and it looks like your y goes from 0 to 3, and your z goes from 0 to 3. So these are all just nice planes that are parallel to the coordinate planes, or I mean 3 of them are the coordinate planes, and then the other 3 are parallel to the coordinate planes. So we'll have a fairly simple setup for these things. Okay, so that's the first surface. Maybe we'll just make a list of these surfaces over here. S2, our second surface, let's let that be y is equal to 0. And this time your variables are x and z, going from 0 to 3 for both of them. And then your S3 would be maybe z is equal to 0, and your x goes from 0 to 3, and then your y goes from 0 to 3. So those are the first 3 surfaces, coordinate planes. This is the first one, S1, S2, and S3. All right, let's continue with the surfaces. S4, let's use x is equal to 3. X is equal to 3, going from your y goes from 0 to 3, and your z goes from 0 to 3. S5 is an xz limit from 0 to 3. And S6 is the top. Okay. Now, as a flux integral, what we're interested in doing is to find this integral over each of these surfaces of f dotted with n ds, capital S. So remember the flux integral, a couple of different looks at the flux integral. We can look at that as a surface integral where we're dotting with a normal vector, or we can do the parameterization. So the reason why I'm interested in doing this is because the normal vectors are fairly straightforward for these things with an outward going normal. So the normal vectors are pretty straightforward. So I think I can just name those normal vectors for each of them, and then we'll see how the parameterization will work out. So our normal vector for the first one, S1, that's the bottom. That's the back side of this cube. It looks like it'd be pointing in the negative x direction. So our n1 for this, let's call it n1 for the first normal vector, is going to be -1 in the x direction, 0 for the other directions. So this will get me a little bit more selective as to how I'm going to fix up my parameterization. So I didn't quite write my parameterization over here, but if I did write it out, your R, instead of u and v, or x and y, I'm going to choose y and z because that's what would make most sense. So R is going to be a function of y and z. The first component, x, is going to be 0, and then the other two components are just the y and the z. So if you change this into u's and v's with appropriate limits that are given here, and use a 3D plotter or something to graph it, you'll see that piece of a plane. Anyways, if I put this into the vector field, the vector field is x is equal to 0, so anytime there's a 0, I would put 0 in, because that's what my parameterization says, and then the y, z is z. But if you look at each of these components, they all have 0, they all have x's in there. So this is 0, 0, 0. I don't even have to do this flux integral here because this is going to contribute 0 to our total. So we can be done with that. All right. Now let's see how the next one's going to work out. The next one is y is equal to 0, so the y is equal to 0 goes out sideways. My normal vector for that, n2, is going to be 0 in the x, -1 in the y, and 0 in the z. My parameterization for this are, and then my other two variables that are left, because y is equal to 0, I have x and z. It'll be x in the x, 0 in the y, and z in the z, so that when I put my function in, My x is x, my y is 0, my z is z. So I'm just looking up here and looking at my parameterization, putting in those values. And then if I dot these two things, I have 0 times x, well, negative 1 times 0, and 0 times the 2xz. So this is going to be another 0 contribution, even before we do the integral. Okay. All right. So far so good. Long. The next one, our z is equal to 0. That's the bottom of our solid cube, and so we have a normal vector pointing directly down. So n3, the third normal vector we're looking at, is 0, 0, negative 1. Our parameterization R is going to be a function of x and y. And so x is going to be x, y is going to be y, and z is going to be 0. And so the function, the vector field, evaluated at this parameterization is going to be x is x, so that's 4x. Oh, this should have been 4 over here also. Anyways, that's 0 anyways. The x, y, and then z is equal to 0, so that just gets knocked out. And again, when we do the dot product, before we even set up the integral, we dot these two things and we get 0, so another 0 contribution. So far those 3 planes have contributed 0 because the planes themselves were 0. Let's see what these will contribute down here. The next one is the front of your cube. So this is the fourth surface. Let's take a look at the normal vector for that fourth surface. That would be 1 in the x direction, 0, 0, because it's pointing straight towards the x direction. Our parameterization this time, kind of like S1, is going to be a function of y and z. But different from x1, instead of 0, we get a 3 here. Now when we take the dot product, or not the dot product, when we put these values into the function, the x's are all equal to 3. So I have a constant, 4 times 3 is 12 for that first one, and 3y, and 2xz. So 2 times 3 is 6, times z is z. But if I look at my normal vector, it's 1, 0, 0, so the other 2 components are gone. So it looks like my surface integral here is not going to be completely 0. It'll be 12, ds, and my s is this parameterization. So this is my s parameterization. I'm going to make this into a double integral with limits from 0 to 3 in the x and 0 to 3 in the y. So in my x direction, 0 to 3 in my y direction, or I'm sorry, should be y and z, dy, dz. So my y goes from 0 to 3, my z goes from 0 to 3. 9, 12, 108. So it's just a double integral. You're integrating 12. You can take 12 out. You integrate from 0 to 3. That would be 3. Integrate from 0 to 3. That would be 3. 3 times 3 is 9. 9 times 3, or 9 times 12 is 108. All right, you got a non-zero here. Let's see what we get for the others. This one, y is equal to 3. That is, which side is that? That's the right side of your cube going in the positive y direction. So n5 is 0, positive 1, 0. That gives your direction, your outward orientation. Your parameterization is x3z. So the x and z are your variables. The 3 is constant in the y. So it'll be your variable x, and z will have limits from 0 to 3. Now if we put that into the function, that particular parameterization into the function, our function is 2 or 4 times x. Our y is x times y, so that's 3x. And our z is 2xz, so 2x and z, 2xz. But when we dot these, the only thing that'll come up is the 3x. So that's going to be your integrand in your surface integral. So this is a surface integral that we're integrating with respect to this parameterization, where x is x, y is 3, and z is z. I only have an x in there, so I'm going to replace that with x. Well, I'm just going to keep it as x. And now I'll have limits going from 0 to 3 in x and 0 to 3 in z. So it's a double integral now of 3x dx. X goes from 0 to 3. And dz goes from 0 to 3. Is it 3x? It's 3x. So integrate with respect to x. That'll be 3x squared over 2. You square that, it'll be 9. 9 times 3 is 27. 27 over 2 times 3, 81 over 2. Is that right? I hope it's right. I'll move on assuming it's right, and then if it's wrong, then that could be the place where it should be wrong. All right, last one. This one, your n goes straight up because it's the top of the cube. So we have a normal vector 0, 0, 1. And your parameterization is x and y and 3. And so put that into the function. We're going to get x is x, y is y, and z is equal to 3. So the z was 2xz. 2 times x times 3. I guess that's 6x. And when I dot this, the first two components go away because of the normal vector, and then we just have 6x. So 6x this time, ds, integrating over this vector, or this surface, where x is x, y is y, and z is 3. X and y go from 0 to 3, so that's our double integral setup. 6x dx from 0 to 3. dy from 0 to 3. So this would be just 81, I think, right? It looks exactly the same as that, except it's multiplied by 2 more. So I'm going to go with 81. Whew. Add them up. 189 plus 81 over 2. And you guys just punch that in the calculator and get an easy number. Anybody? Four, 5.9 over 2. All right, let's check that. I did those integrals in my head. Was that, it might have been wrong. So don't do integrals in your head. Is it right? Oh, that's right. Okay. Well, clearly, this is a lot of work. And if you're verifying something, this is half of your work. The other half is using divergence theorem, where you take the triple integral of a div of the vector field. So let's see if we can, see if we can redo this problem looking at the other side of it. So instead of doing the flux, we're going to trade it in for a triple integral. Now, when we think of triple integrals, we think, wow, that's 3 integrals. That seems kind of hard, huh? Well, there's a couple of things that are happening here. One thing that's happening is you're taking the derivative of a vector field, which might have a chance of looking a little easier than the original problem. So that's one thing. The other thing is that this surface that we started with was 6 sides of a surface, and if we look at that as the boundary of a solid, then we have a solid that we're going to integrate over. That seems a lot easier, I think. So your solid E is a solid that can be easily described with 3 simple inequalities, which will end up being your limits for your triple integral. So immediately there's 2 things that is going to make this easy. One is that you're going to integrate just one integral because there's only one solid instead of 6 surfaces. 2, you're going to take the derivative of something. And usually when you take derivatives of things, it becomes a little bit easier. So that's the second part. Let's take that second part and try to figure out what the div of f is equal to. So the div of f takes each of those components and takes the derivative of the first component with respect to x, the derivative of the second component with respect to y, and the derivative of the third component with respect to z, and then you're just going to add them all up. So you're going to get a scalar function out of that. That's good because we can only integrate a triple integral, integrate scalar functions. So 4x with respect to x is 4. xy with respect to x is y. Wait, 4 xy. Let's try that again. xy with respect to y is x. And 2xz with respect to z is 2x. Did I do that right? That's the div. And the divergence is really just 4 plus 3x, a simple function that's going to go in your triple integral. All right, let's integrate. So we have 4 plus 3x, and let's take the integral of this with respect to x. And with respect to x goes from 0 to 3. Then we'll take the integral of this with respect to y. Y again goes from 0 to 3. And then with respect to z, where z goes from 0 to 3. I suppose there's no y's and z's here, so we can split this up to the y and the z separately and just focus on integrating four plus 3x with respect to x. So that's 4x plus 3x squared over 2 from 0 to 3. 12 plus 9, 27 over 2 times 3 times 3. So I hope this, yeah? What was the answer again for? Maybe that worked out. So this was a lot easier, yeah? You think? So that's it's like that's a pretty powerful theorem. Yeah.
So what does the number represent exactly?
Well, it represents, it's a flux of this vector field. So it represents this vector field. If we look at it from the flux side of it, it represents how much of the, I guess it's not work, how much flow from the vector field is passing through this cube. Yeah, it's like a flux. It's like we talked about the flux with when you take a net, like you're fishing, you take a net and you lift it up. How much flow of water is going down? So you can think about that vector field as just going straight down, but your net is curving. So you can think about that as a flow passing through a solid. In this case, it's a cube that goes outside of the cube, flowing because they're outward normal. You can look at this as an energy field or a vector field or a force or magnetic field or something. How much of that magnetic field is passing through the cube. Okay. Let's see if we can do another problem. This time I hope we don't have to verify anymore. Just verify, verify, verify. Oh. Let's do number 7. Fat sphere. What's a fat sphere? I don't know if I want to do a fat sphere. All right, getting too crazy here.
So
I'm going to use this, my easier plotter. Not really a sphere. So it's up to the power that's changing the shape of this thing. Oh, I can't have fractions for the power. Can I have odd numbers? No, I can't have odd numbers either. Anyways, that's going on a tangent. Let's look at number 5. It says to use the divergence theorem to calculate the flux of F across S, and then here's your F, and then now your S is going to be what we want to focus on. As a cylinder, Y plus Z, Y squared plus Z squared is equal to 9, so it's going along the X axis, and we got a couple of planes. These are just regular flat planes that cut them off, so there's no weird angles or anything like that. So we have cylinder cuts off over here at -3 and a +1. So it looks like it's a cylindrical coordinate problem. I'll probably want to use cylindrical coordinates. And they don't talk about the orientation here, so we'll just assume that the orientation is outward orientation, which allows us to, if they force you to do an inward orientation for any of these divergence theorem problems, then you just calculate the triple integral and put a negative in front of it. That's all. All right, so if you were to do the flux integral directly, you would need to do 3 integrals. So you'd need to do one for this flat surface, another one for the other flat surface, and then another one for the cylinder itself. So this is a triple integral, or a flux integral that would come in 3 parts. And I'll make up a notation where we're adding up 3 flux integrals to get this one flux integral that we want. But of course we're not going to do that. We're instead going to use the divergence theorem, where we're going to try to describe the solid, which is a nice simple cylinder of the div of F dV. And since we're integrating, since this is happening kind of like on the YZ plane, we're probably going to use our YZ for our variables. Well, but first we have to look at the div, so let's figure that out. So the div of F is going to be a scalar function, the derivative of the first term with respect to x. That'll be 3y squared. The derivative of the second function with respect to y, there's no y's in there, so that's just 0. And then the derivative of that last one with respect to z, that would be 3z squared. This looks like it's a setup. to an easy integral. Okay, so this is our div. That's what's going to go inside of the function. Now we need to try to describe this surface. So to describe the surface, it looks like our x and our y's and our z's can come together like this. Now the x is fairly straightforward. X goes from -3 to +1. But the y and the z, if you look at the shadow that this is going to make on the yz plane, it looks like the shadow that it's going to make on the yz plane is a circle. And so on the yz plane, instead of trying to figure out, the square roots of all that stuff, why don't I just say on the yz plane you're dealing with a circle? And what we're going to do is we're going to either look at this as cylindrical coordinates or set up the triple integral and then break it down into polar coordinates in 2D. I think it doesn't matter as long as you're okay with writing the cylindrical coordinates with x is equal to x. I think we did this before, right? We had x is equal to x, and then the y is the one with cosine, and the z is the sine. So x equals x, y is equal to r cosine theta, and z is equal to r sine theta. And then that'll give us y squared plus z squared is equal to r squared. So let me just set this up over your solid E. We have 3 y squared plus z squared dv, sorry. And now let's go directly into cylindrical coordinates with this business. So I'll have a 3r squared, that's my integrand here. And then as part of my dz converting into cylindrical coordinates, I'm going to have an extra r. And then normally I have a dz, dr, d theta, but then instead of a dz, I have a dx, because my x is x now. So x goes from -3 to 1. And this is a circle of radius 3, and we should have established that before we wrote the integral. So your r is going to go from 0 to 3. And then your theta is going to go all the way around. So back to our integral. We can do r first, dr, and that's 0 to 3, and then d theta from 0 to 2 pi. Okay, so I think that's it, pretty much. So we integrate, we can split up the integrals. We have 0 to 2 pi for d theta. Our x also, there's no x's in here. We can put an x integral from -3 to 1. And then move the 3 all the way out if you want. You got r cubed dr from 0 to 3. So what is this? This is 3 times 2 pi times what is this? 1 minus -3, is that 4? And then now we have r to the 4th over 4. So we have 3 to the 4th, 3, 6, 9, 81. Six times 81. 486 pi, I would guess. Okay. 2 for 2. Okay, we good? All right. So there's an interesting twist to Gauss's theorem when we're working on things. And let me see if there's a problem like that in the homework set or in this. Oh yeah, number 12 would be the example that I was looking for. So remember, the part of the conditions for Gauss's theorem is that the surface has to be closed. Okay? Let's take a look at this problem. Use the divergence theorem to evaluate the flux of F over S, where S is the top half of the sphere, period. Top half of the sphere. So the top half of the sphere doesn't automatically imply that it's closed in the bottom. It just says it's the top half of the sphere. So Gauss's theorem allows us to do this change from a flux to a triple integral if we have a closed surface. So if it's not closed, what do you think we can do to use Gauss' theorem?
Figure it out for the whole sphere.
Or instead of the whole sphere, just close it with something simpler than the bottom half of the sphere, like a disk. Right? So that would work. I mean, the bottom half of the sphere would work too. If in some cases that could be easier. But what we want to do is we want to try to get, if we're going to enclose an open surface, we want to try to close it up with the simplest surface as possible. So here's what we have. We have the top half of the sphere with an open bottom. Okay, so note S is not a closed surface. First compute the integrals of S1 and S2, where S1 is the disk that closes this sphere. And if we put a downward orientation, then that would have a downward orientation. Okay? So here's the deal. Gauss's theorem says that we can do this switch from a flux integral to a triple integral of the div, provided it's a closed surface. We don't have a closed surface, right? Okay, I'm messing up their notation. Let me see if I can do their notation. S2. This should be S2. S2 is the combination of S. So let's say the top hemisphere here, top hemisphere only, is S. That's the original flux integral that we want to compute. What we're going to do is we're going to enclose the bottom here with a surface they're calling S1. So bottom, I'll call it a disk, that encloses this surface so that we have a closed surface now. So S2, as they say here, is a combination of S1 and the union of the original surface. So we want to, essentially, what we want to do is we want to solve for S. So let's do the big algebra, big picture algebra of this thing. So S2 is going to equal to two integrals, two flux integrals. One of them is the flux integral of S, that's the top half, plus the flux integral of S1, that's the bottom disk. And this is supposed to be equal to the triple integral. Okay, so this is a big picture that we have. This is what we want. We want this. This, we're saying that we're pretty confident that we can get that quite easily. And this, we don't know this, but provided that we chose a simple enough surface to deal with, this might be easy to compute also. Okay, so all we have to do is find this, find the triple integral, find the easier flux integral, and then subtract them, and we would get what we're looking for. Does that big picture make sense? And then we'll dive into each of these. We'll dive into these two integrals separately. Does the big picture make sense? All right. Yes, it makes sense. Okay. Now that you guys all agree that it makes sense, let's do these integrals separately. Let's do the triple integral. We want the div of this thing. So it's the derivative of the first component with respect to x. That looks like it's z squared. The derivative of the second component with respect to y, this looks like it's y squared. And the derivative of the third component with respect to z, that looks like it's x squared. Hey, this is like a setup. So in our triple integral, we have x squared plus y squared plus z squared. That's what's going to go inside of our triple integral. And our E is the top half of the sphere. Radius, radius, radius 2. So I'd be happy to go just jump straight into spherical coordinates with this. Well, I guess first I should set up the triple integral E x squared plus y squared plus z squared dv. And then now let's go use spherical coordinates. So x squared plus y squared plus z squared is going to be rho squared, and then the dv is going to be rho squared sine phi, automatic, that's Jacobian. Now, if we integrate with respect to phi first, I should have figured it. I keep forcing people to figure out the inequalities before they set up the integral, but I'm getting really excited. I just want to set up the integral. But you should really set up the inequalities. Rho goes from 0 to 2, that's the radius. Phi goes from where to where? You know, it doesn't go all the way down, right? So it only goes to pi over 2. And then theta goes all the way around to 2 pi. All right, there, limits. So our phi, our rho goes from 0 to 2. Our phi goes from 0 to pi over 2. And then our theta goes from 0 to 2 pi. Oh, what a mess. So I'm going to integrate from 0 to 2 pi my d theta. That's just going to be 2 pi. I'm going to integrate from 0 to pi over 2 my sine phi, d phi. If you haven't already seen this, the integral is going to be 1. The integral over 1 arc of the sine function is 2. So this is half of the arc, is 1. And then the last one is going to be an integral from 0 to 2 of rho to the 4th over, or d rho. So I got 2 pi over here, and I got 1 for this one, and this is rho to the 5th. So 2 to the 5th, computer science people? 2 times 2 times 2 times 2 times 2. Is that 32 or 64? 64. Have you guys ever played the game 2084?
2048.
2048.
Oh, you can talk about that. Yeah, that's a really fun game.
Yeah, so it's like all powers of 2. All right, where are we? Oh, here, we're done. 128 pi over 5. So that's this part, but remember, you have to subtract out that imaginary disk that you put on, right? Because that wasn't part of the deal. So let's see how hard that's going to be. We're going to parameterize this disk. Let's take that disk and bring it on over here. This is a disk where z is equal to 0, and then x and y is just this disk, radius 2. And we want a downward normal to have the outward pointing normal, so we can get that set up also. N is equal to, because it's going to be a flux, right? So we want to dot it with a downward normal. 0, 0, negative 1. And with the zeros here, that will wipe out a few things for us. So what we want to do is we want to do our parameterization. Our parameterization is going to be, well, it's going to be x, y, 0. R is going to be x, y, 0, because it's 0 and a z, right? And so if we look ahead to our function that we're eventually going to dot with n, the first 2 components of n are 0, so I know when I dot that, I'm not going to get anything out of it, so I'm not even going to bother computing that. But the last one I will need, so let's figure out what the last one is. The last one is y cubed over 3 plus sine z, where z in our parameterization is equal to 0. Why do we use the, say it again? This one? Oh yeah, yeah. We have, because we need this vector field over here. So normally I would have put in x and y and z 0 for z, but I didn't even bother looking at that because when I'm going to dot these two things.
You dotted it with J,
Dotted it with J. Oh, this is right. Oh, my bad. Okay, thanks. So this is what I want. So 0, so x squared times 0 plus y squared. So I still get a y squared. So when you dot this, you get y squared, negative y squared. So f dotted with n is negative y squared. So I have the flux integral is going to become a surface integral with negative y squared in there, and our domain D is that disk on the x and y. So at this point, I'm going to go to polar coordinates in x and y. So polar coordinates I'm going to go to polar coordinates with r going from 0. What's the radius to? And theta goes all the way around to 2 pi. So my y would be, what is it, negative sine squared theta times r dr d theta, because I'm doing the polar coordinate business. And r goes from 0 to 2, theta goes from 0 to 2 pi. And I can't break this up, and that's not an easy integral I can do in my head. So, well, I can break it up, but the sine squared theta is like a double angle business that you have to deal with. Unless you guys punch in your calculator and tell me what you get. So 0 to 2 of r dr, and integral from 0 to 2 pi of minus sine squared theta d theta. Say it again? Oh yeah, r. Ooh, thanks. All right, guys, I'm trying to rush. I'm sorry. Negative r sine theta squared. So that gives 2 more r's here. All right. Is anybody doing this in their calculators, or should I call Wolfram? Hello, Wolfram? Calling Wolfram Alpha. Wolf. So I basically want to integrate sine squared theta to, did we go all the way around 2 pi? So there's a minus sign there, and then r cubed is r to the 4th. 2 to the 4th power is 32.
Yeah.
So r to the 4th over 4, 32 divided by 4 is 8. So this is pi. So 2 to the 5th is not 64. It's 32. Dang. You said 32? So this one, 2 to the 4th is 16, and then we divide by 4, because when you integrate you get 4, so this would be 8. So minus 8 pi, we subtract that, 64 pi over 5 minus negative 8 pi. And that should be our, I don't know. Should be 4? Okay. So 64 over 5 plus 4 pi. Let's see if we can put that in. Where? Here. 64 fifths minus 4, or plus 4. Plus 4, and then pi. We were 2 for 2. I don't want to check this. We got a perfect record. Let's check it. It's okay. Even the Warriors lost, so I guess it's okay for us to. Sweet. All right, 3 for 3. Look at that. Whew. So that's Gauss. That's Gauss's theorem, and so this little trick about covering up an open surface so that we can use Gauss's theorem, provided that this integral, this flux integral that we had to do, was fairly easy compared to what we would have had to go through if we would have tried to integrate over that surface already. So, so yeah, this is Gauss. Now, tomorrow, what we're going to try to do is we're going to try to unify all these theorems together. So we're going to look at the different types of integrals that we have, some shortcuts on things, and some interpretations of things, and then everything is going to be the fundamental theorem of calculus. So it would be a good idea, I know your homework is due soon, it would be a good idea to try out some of these problems for your homework before tomorrow, so that when we start talking more about integrals, it'll make a little bit more sense and it'll mean a little bit more to you what you're doing. So do some homework tonight. Okay, bye.